Okay. All right, here's the link. Here is the link. Let's hear what it sounds like on the YouTube. So here is what I see. When I wait for the signal to come in, I just sit here and wait, and I can look at the notifications. There you go. There you go. All right, mic is good. We're in good shape. So then I mute it. Let's mute. Very nice. Now let's go to this guy. So we were in the midst. Oh, that's the previous video. That's not important. Actually, that's not important. Oh, we need to give it a name. So what were we doing? Oh my God, this is so difficult. Can I open it in a separate tab? But I don't want to bore you. Well, we did a little bit of calculus of variation. Variation or variations? I think variations. Let me check. Where's the title? Calculus of variations. Variations. Not with an X, with an S. Yes. Okay, so we did that. And then we did, what is this? Pythagorean theorem, not important. Yeah. Okay, so this is already, okay, then we wrote some papers. Write papers. Okay, what else did we do? So we also, that's writing the papers about the ether and detecting the ether. That's good. We made a little bit of progress. That's good. That's good. Then we read Einstein's paper. That's good. And then we discussed, this is basically halfway through, we went into brain research a little bit. Where is this? Here. So we did neuroscience. We did pain and pleasure, and then we researched dopamine. Dopamine and the dopamine pathways, which was fairly interesting. Yes, it was fairly interesting, and I'm gonna hit the editor because there's some stuff I need to take out. All right. Okay, so the next thing that I wanted to do is, I guess, get back to this guy. Okay, let's listen. I want to continue studying calculus of variations. He seems to be really good at it. So this equation, what is this? This seems to be the red equation, but it somehow is defined over two lines, I guess. So he says the f of x as defined from x is 0 to x is 2, but this has 2x. I think this is the red line. This is just the red line. And then this line, this is the integral. This is the ds. But I don't think he's showing, oh, this is the answer. This is just a calculation. Oh, this is just integrating a definite integral. Okay. And then he created h of x. This is the black function. So it's defined for x is between 0 and 2, same as before. But this time, the equation, the function is negative x times x minus 2, which I explained. So it ends up being negative x squared plus 2x. So this is 2x. So this it's a strange, it's a parabola, but it's skewed because we're adding 2x to a negative x squared. It doesn't look skewed. It looks perfect, but it should be skewed. I don't know why we can't see that it's skewed. It's really strange. It shouldn't look like this. I don't know why it looks like this. Anyway, and then we have wiggle of x is f of x, which is the first guy. So it starts with f of x plus a, which is 1.22, and we're able to modify a, multiplied by h of x. As we defined before, this is h of x. H of x is the eta. This is our eta. This is our function. So we are going to want to take the original function f of x, and we're going to want to add to it h of x, not h of x, I'm sorry, wiggle of x, w of x. We're going to add to it w of x. No, w of x is f of x plus a times h of x. Okay, so we're going to take f of x and we're going to add to it h of x times a, and we're going to manipulate a so it could go from negative 2 to positive 2. Okay. And then we're going to take a very similar integral to the first one we did. This one was directly of f of x. This one is going to be of wiggle of x. Wiggle of x is the original f of x, but with the additional eta times a. Okay. And so this one is 4.47. This is 4.77 because this is the wiggle. And the wiggle, we have the a is 1.22. So it's not, right? If this is 1, if a is 1, no, if a is 0, then eta has no influence, h has no influence, then it's the original function. So a is 0, we should get, instead of 4.77, we should get 4.47 over here. Okay, let's see what he says.
I'm taking this red thing and I'm wiggling it by a certain amount of the black thing, and I can change.
Okay, this is now, I don't understand why h is symmetric. This is so strange. I don't understand. Anyway, so this is the addition. This is the red plus the black is the blue or purple. Okay, this is the wiggled function, the w function.
Change the amount.
And as he changes it, it grows, but when it goes to 0, it should be identical to 4.47.
And you can see that, right, sort of perturbs the red function in just a little bit. What's neat about this setup is that I could use different functions for h of x. Like here's a wigglier one. How about the sine of 2 pi x? All right, well, so now.
So the sine of 2 pi x, it has to conform to being 0 at the end points, which are 0 and 2, because the original function, we're looking at it from 0 to 2. So it adheres, it conforms to the requirement. And this is good. This is very nice. So let's see what he says. So again, he's going to wiggle a and see, right? He wants to end up with 4.47.
You can really see that's really a wiggle. And I again have control over the amount of the wiggle. And I could get wigglier, right? I could put any function in there that I want and still end up with some purple curve that connects the 2 points that it's supposed to connect. What's more, I have asked for the arc length of the wiggle, and you can see it's in general going to be a little bit larger than the arc length of my
It's always a little bit larger than the original.
minimal thing, unless, of course, A happens to be 0, and then they coincide. Okay.
When it's 0, they're both the same. They're identical. Amazing.
Okay, cool. So that's what's going on here. And here's my point. If I throw the wiggle into the functional, here's what I get. And truly, this is
so if I throw the wiggle into the functional, so the wiggle is just the original plus the functional. Well, this is a better way. So the, what do you call this? This is, what do you call, I forgot what you call this. Jesus, how quickly can I forget? J is a functional? Yeah, the functional of any function gives me the arc length. Okay, so the function is w. W is y plus a eta. So the integrand is y prime plus a eta prime. 1 plus square root. Okay. This is truly a function of a. Oh, wow. So the functional of w is a function of a because a is the parameter with which we're playing around. Fascinating.
function, a regular plain old R to R function.
Right, because the functional of w, it's a number, but as I modify a, I get a different number. I get a different real number output. So there is a map of j as a function of a. That for each a, there's a different output. For each a, there's a different output. I mean, for each a, there is an output. I don't want to say different. There could be many a's that give the same output. That give identical output. But for each a, there is an output, not necessarily a unique output.
Of the amount of wiggle, of variation, that is.
That's why he kept saying amount. So a is the amount of wiggle, the amount of eta. Okay.
And so if that's true, right? So I can write it literally as j.
Wait, what just happened? Oh my god.
Okay, cool.
Okay.
So that's what's going on here.
Here's what
plain old
something
variation
dark side.
J as a function of a, and here is what it would be.
So here is j is a function of a, which is identical. There should be no difference. There's no difference.
And if that's true, then I can take a derivative with respect.
So I can take a derivative. Finally, someone who's really explain. Everyone else skips so many steps. So I can take a derivative with respect to a. Wow, because I'm holding everything else constant. That's incredible. So I can take, whoever invented it is like, how did you think of all these details with respect to a? Fantastic. So I can take a derivative with respect to a. If y, what would it look like? So eta prime is going to come out. That's going to be incredible because it's a definite integral. So do I need to first integrate? I can't because I don't know anything about y. It's any y. We don't know anything about y. If y corresponds a equals 0, is a minimizer, then j prime at 0 equals 0. Let's see what he says.
Back to a. And what's more, if my original function is a minimizer, right, that's the one that corresponds to a equals 0, which means that j prime at 0 ought to be 0.
I don't know what that means. What is a minimizer? I never heard of a function that is a minimizer. If y is a minimizer, what does that mean? What is a minimizer? Anyway, he says j prime at a equals 0 is 0. Yeah. Because if a is 0, then we're removing the effect of eta, and we're back to just y, and that has to be a minimum.
And so I feel like that's a technical handle that I can use to calculate anything in this weird situation. Okay, well, that's going to involve differentiating an integral.
So now we're going to differentiate j, get the value of, we're going to say j at 0 equals 0, or the derivative of j at 0 must be 0. So the derivative with respect to a of this thing,
for which we're going to need to use a fun trick.
But he's not going to say is equal to 0. Why is that? The derivative of j at j equals 0, the derivative of j, meaning j prime or j sub a, at 0 is 0.
Called differentiating under the integral sign, or the
Leibniz integral rule. Sometimes this is called Feynman's integral trick, but he's kind of a jerk. Feynman is a jerk? Who's a jerk? The trick is a jerk? As long as the integrand is continuous, okay, the derivative of this thing, of any one of these guys, is equal to the integral of the derivative. So so the derivative and the integral are commutative operators. What's going on with Bitcoin? Okay, so the derivative, of course, no one is watching us. No one in the universe is watching us. So the derivative, right? So the derivative and the integral, even though, or maybe because, but it's a function of x and a. This is here, it becomes a partial derivative with respect to a, but this is the total derivative with respect to a. This is really weird. The derivative of the definite integral with respect to a is equal to the integral of the partial derivative with respect to a of the function. Well, we would have to prove it, but if we have the proof, then assuming we have proved it, yeah.
The Leibniz integral rule. Sometimes it's called the Feynman integral trick, but honestly, he's kind of a jerk, and so I don't want to stick his name on it. As long as the integrand is continuous in the region that we
Why is he a jerk? Could you tell us?
Care about, which I promise it is, you can interchange the order of the integral sign and the derivative sign, but then we need to think of the derivative sign as a partial derivative because now there's one more variable going on.
Because here this is a function we're integrating over x, over dx, whatever, over x. We're getting a number, we're getting a value. It's a definite integral, so we're definitely getting a number, but a is a variable. So within this definite integral, we're not telling anyone what a is. So a remains an independent variable. But if we commute in the derivative, then it's partial because x is still independent as well.
Reminds you of Fubini's theorem, that's because it is basically Fubini's theorem. If this reminds you of Clairault's theorem, it's basically Clairault's theorem. I'm not going to prove it. You can think about what a proof would look like. It's not too bad. All right, so let's do this calculation, and I'm calculating toward the idea that j prime of 0 ought to be 0. All right,
Very
so
interesting. So j prime of 0 ought to be 0. So this is the derivative. That's fine. And we said we can commute in, and then it becomes a partial derivative. And then, okay, so we're going to go and do it.
Got the derivative of my function of a. I've done my differentiation under the integral sign trick. Let's do the calculation here. Works out to be this, and if I simplify a little.
So now we're taking the derivative, the partial derivative with respect to a. Okay, it's doable. Because y prime is not a function of a, and eta prime is not a function of a. These are basically, but they are functions of x, but we don't care about that. Right now, we're only dealing with the derivative. We don't care about the integration. So the derivative of something to the 1/2 is 1/2 times that thing to the negative 1/2 times, this is 0, and this is 2 times this thing times eta prime times eta prime, and then dx, because we're inside an integral, that's fine. And then the next step is, so he says y prime plus a eta prime at the top. Well, okay, so this is just, okay, so 2 and 1/2 cancel out. Y prime plus a eta prime is at the top. Eta prime is on the right. And the negative 1/2 goes downstairs and becomes positive 1/2. That's fine.
Here's what I get. And now I want to think of this when a equals 0, right?
Oh, very good. So just plug in a equals 0, no?
And so I'm thinking of evaluating the derivative at the point a equals 0, and I'm told that I'm.
So this is, I can't believe I'm learning this from a math channel, and it's the simplest explanation. Every explanation has been basically impossible by everybody else, and everybody just tries to simplify. This guy, he's not trying to simplify, he's just trying to be correct, and it just ends up being the simplest, being the most straightforward. Okay, so a equals 0. So we want to calculate a definite integral over dx. So y prime is a function of x, eta prime is a function of x. A is not a function of x. A is a constant. So if a equals 0, then the eta goes away. I mean, this eta goes away, and this eta goes away. But this eta stays, which is very nice. Eta prime stays. So it's going to be y prime divided by 1 plus y prime squared square root times eta prime dx.
Supposed to get 0, right, by my hypotheses. And here's what
And that should equal 0. That whole thing should be 0.
I really get when I substitute 0 in.
So there we go. So y prime, correct, over the square root, correct, eta prime, correct, 1 plus y prime squared, correct.
All these a's die, and they take those eta primes with them that are inside, and the only eta prime that's left is this one that lives out here. Okay, cool. Boy, this is still just a mess, though. I don't really know what to do with this. What we're going to do with this is we're going to need a lemma, and it's called the fundamental lemma of the calculus of variations. And I love whenever something that's called
What is a lemma? Why do they have all these words?
fundamental comes up. Here's what it says.
That
If you
what
love
comes up?
whenever something that's called fundamental comes up, what we're going to do with this is we're going to need a lemma, and it's called the fundamental lemma of the calculus of variations. And I love whenever something that's called fundamental comes up. Here's what it says. If you integrate a continuous function.
Okay, let me read it. Suppose m of x is continuous if the definite integral of m of x times eta x dx equals 0 for all variations of eta, then m of x is defined as 0. Or m of x must be 0, I guess. Again, suppose m of x is continuous. If this definite integral, where we have m of x times eta of x dx equals 0 for all variations, this is the fundamental lemma of calculus of variations. So eta, I guess, is the variation function. M, let's say, is the original function or something, because it's not. It's m prime stuff and eta prime. It's completely different. For all variations eta, then m of x is 0.
Against a variation, and you get 0, no matter which variation you choose, well, then the function has to be identically 0, right? The constant function 0. Okay, let's see how the proof is going to go. The proof is fun. It relies on a little bit of analysis, but nothing too scary.
Let me hear it
right?
again.
The constant function 0. Here's what it says. If you integrate a continuous function against a variation and you get 0.
If you integrate a continuous function against a variation, what do you mean against a variation? It looks like you're integrating the product of a function with a variation. Okay, so that's defined as against. And you're saying it's 0. I'm just trying to think what it looks like. Any function, just draw in your mind a function from x1 to x2, but it's multiplied by eta, which is a variation, some variation like cosine or something. Okay. So it's the original function multiplied by cosine. So it's a mix of cosine. It's a cosine of the original function. Okay, and then you integrate a definite integral. It's some area under the curve. Okay, but you're saying no, there is no area under the curve. It's 0. And the variation is non-zero. Well, the only way that's possible is if the function is 0. Why? There could be positive and negative areas, right? There's area is I don't remember. When you do area, right? There's area under the curve and over the curve. So under the curve is positive area, over the curve is negative area. So if eta has over and under, over and under, over and under, and it's multiplied by this, let's say this is just y equals x. And this is cosine. So it ends up just being, or let's say y equals 1. And this is cosine. So it's just cosine. So the area under cosine is 0. So the area under cosine is 0. That means m of x is 0. No, it's 1. I don't understand. Let's see what he says.
No matter which variation you choose, well, then the function has to be identically 0, right? The constant function 0. Okay, let's see how the proof is going to go. The proof is fun. It relies on a little bit of analysis, but nothing too scary. We're going to do it by contradiction. We're going to suppose not. We're going to suppose that m is not the constant function 0, which means that somewhere it's got to either be above 0 or below 0. Without loss of generality, we'll say above. There has to be some special x star where it's above 0.
What is W
Okay,
log?
and then our hypothesis was that the function was continuous.
Let's see what.
Above. We're going to do it by contradiction. We're going to suppose not. We're going to suppose that m is not the constant function 0, which means that somewhere it's got to either be above 0 or below 0. Without loss of generality, we'll say above.
Without loss of generality. Okay. Without loss of generality, I don't know what that means, that m of x star is greater than 0. So there is some x, that x is above 0. Okay, this is the original, because we're assuming it's not 0, so there must be some x where m of x star, there must be some x star such that m of x star is greater than 0. It's non-zero. Okay.
There has to be some special x star where it's above 0. Okay, and then
couldn't it be below 0 just as well? Didn't he say that it could be below 0?
We're going to suppose not. We're going to suppose that m is not the constant function 0, which means that somewhere it's got to either be above 0 or below 0. Without loss of generality, we'll say above. There has to be some special x star where it's above 0. Okay, and then our hypothesis was that the function was continuous, which means that I can take that point where we're above 0 and I can fatten it up into a whole little interval where m is greater than 0. I think maybe a picture would be helpful here. Here's my...
It's fine. I mean, if you're saying there is a point x star such that mx star is greater than 0, that means there must be an interval because the function is continuous. There exists an interval CD around x star on which mx is greater than 0. That's fine. That's fine between C and D.
Like x-axis, right? Zoom. Beautiful. That was nice and straight. Here's my function m. If it's non-zero somewhere at this x star, well then it has, since it's continuous, it has to be non-zero on a little interval around. All right, cool. So we're gonna say we're gonna make up a function.
Let eta x be 0 for all x not between C and D. So eta of x is 0 everywhere for all x where x is not contained between C and D. So everywhere except for C and D, it's 0. Okay, it's a discontinuous function, eta of x. And it's going to be x minus c times d minus x. I don't know why this specific function. Such for all x, such that x belongs to the interval between c and d. So between C and D, so example, at C, C minus C is 0, D minus D is 0. But what about exactly between C and D? D minus C over 2. I don't know what's going to happen. I don't know what this looks like. So as from at C, it's 0. But then as we go above C, so this becomes positive. But we're still below D, so this is positive. So I think it's positive, this thing, no?
Eta, which is 0 outside of that interval, and then it does this little parabola thing on the interval. So I'll sketch that function. Looks like this. Here is C, here is D. We're going to go
It's gonna be 0 at C and 0 at D, because at D this is 0, at C this is 0, C minus C, and D minus, X equals C is C minus C, and X equals D is D minus D. So it's going to be 0 and 0. I don't know what it looks like between.
0, parabola, 0.
Very nice.
So this is clearly a variation, right? It satisfies our definition.
Okay.
It's piecewise C2. It's 0 at the endpoints because it's 0 off of this.
Piecewise C2 means it's integrable. Sorry, we can take derivative and second derivative. Yes.
Small interval. All right. So by our hypothesis, we were integrating m against this this variation, and we were getting 0. Okay, I'm going to split up this integral into 3 pieces.
So you're saying eta is non-zero on the interval CD, but you also, well, you're not saying x1, x2 is CD. Oh my God, this is becoming so meticulous. This is just to prove the lemma.
And I bet you can guess what those pieces are. You're right. They're precise.
So he's splitting it up to x1 to C, C to D, and D to x2. But everything else remains the same.
The piece between where we start.
So all we care for is this guy. From C to D, we have concluded that mx is above 0 and eta is above 0. So this is non-zero. The eta is 0 before C. Eta is 0 after D. So these two are 0. So this is non-zero. So this must be non-zero, yet we assumed it is 0. So we've reached a contradiction.
And C, the piece between C and D, and then the piece between D and where we end. All right, and the reason
Let's hear what he says.
I'm going to split up this integral into 3 pieces, and I bet you can guess what those pieces are. You're right. They're precisely the piece between where we start in C, the piece between C and D, and then the piece between D and where we end. All right, and the reason that I'm doing that is because eta of x is in fact 0 on this interval
before
and
C,
on this interval.
After
and so
D.
these two integrals will die.
Yes.
And then what's more, this one, right, eta of x is positive because it's the upward parabola by our choice. And m of x is also positive on that interval. So I got a positive thing times a positive thing. If I integrate that, I'm going to get something positive. There's my contradiction. 0 is greater than 0.
Yes.
Okay, cool. So we have proved the fundamental lemma. If we integrate against a variation and we get 0, no matter which variation we choose, then our function is identically 0. Okay, here's a...
That's incredible. So if you integrate against a variation, the function must be 0, and you get 0, the function must be 0. We just proved it. We assumed it's not. Okay, I'm going to go with this. Okay, corollary.
Corollary. You may have noticed that we didn't have an eta in our previous thing. We actually have an eta prime. So let's see how that changes what we have. If I have a big M that's continuous, and I'm integrating big M against an eta prime for any variation eta, well then m of x, big M is going to be a constant function. Okay, I bet you can guess how this is going to go.
Jesus Christ, he actually goes through proofs? My God. How do you live your life? You really prove everything? Jesus. I'm used to just everyone saying, and we're not going to prove that. Look it up. Go kill yourself.
Here's how it's going to go.
Okay, integrate by parts. So the integrand, so again, we are, this is given. So we want to prove that m of x must be 0 something.
We're going to integrate by parts. I got to choose a u that I can take the derivative of, and I got to choose a dv that I know how to integrate. Probably what I'm going to choose for dv is eta prime dx.
Okay, so dv, we're going to replace dv with this guy. Okay.
So that v is eta of x.
Okay, so v is eta of x, yes.
That leaves my u to be big M. My du would then be big M prime, which I'm just going to write as little m.
That's
for
okay, so du is little m. Okay.
Reasons. Okay, and then if I throw this into my integration by parts formula, here's what I get.
So integrate, I don't know, integration by parts. So this is basically, I don't remember integration by parts. M times eta. Let me just move your mouse. Okay, m times eta. This is m times eta minus the integral of eta times m. Okay, I mean, we can easily check this. If we take the derivative of this, we should get this. The derivative of this guy is a big mess. Interesting. Okay, whatever. I mean, I'm just going to assume that this is integration by parts and everything is fine.
U, here's my v, and then the integral of v du. Eta is 0 at the endpoints, and so this piece dies, which
wow,
is nice. And so I just end up with...
okay, so 0... Okay, this is 0, so this is negative. This is just a repeat. Okay, replaced m with eta.
Negative this integral. But look at this. This integral is the integral that we just
proved. M must be 0. So capital M must be a constant.
We're in the situation of with the fundamental lemma.
We've landed in the situation of the fundamental lemma, so we can conclude that m equals 0, so m is constant.
We can conclude, therefore, that little m is 0, and little m was the derivative of big M, and so big M has to be constant. Okay, neat. What are we going to do with that?
Consequences of j prime at 0 equals 0 is this thing.
Well, here's what we have. We have some thing that is multiplied by the derivative of some variation, and we're integrating that, and we're getting 0. That was the consequence of saying that j prime of 0.
So we were already here, I think, and then we detoured for the lemma.
Ought to be 0. And so that means by the fundamental lemma, the corollary of the fundamental lemma, I should say, this thing that's integrating against eta prime ought to be...
Okay, so the integrand without the eta must be a constant. Yes, that's the big M. The big M must be a constant. Okay, we proved that.
be some constant. All right, well, let's do a little bit of algebra. Here is what happens.
Okay, so y prime is equal to c times 1 plus y prime squared 1/2. So 1 prime squared, we're squaring both sides, is c squared. 1 plus y prime squared. Y prime squared is equal to c squared. We're multiplying it out, plus c squared, y prime squared. This is 2 steps at once. Who's calling me? Probably gonna get an email right now. Well, usually the email comes first. Okay, so what is he doing now? This is y prime squared, but 1 minus c over here. Why is that? Well, c squared. Oh, look, there's a y prime squared and y prime squared. Okay, so it's 1 minus c squared. Y prime squared is equal to c squared. So y prime squared is equal to c squared over 1 minus c squared. So y prime is equal to k, some constant. Yeah, it's just some constant. That's correct.
And what we end up with is that y prime is some constant, like c squared over 1 minus c squared, but I don't really care because c was arbitrary. Let's just rename that some new constant k. If y prime is a constant k, well, then y is for sure a straight line. Hooray, we have
Y is a straight line. Oh, which is what we wanted to prove. Right, so we're showing that our method worked.
proved what we thought was true. So here is what we have proved.
That a straight line is the shortest path between 2 points, correct?
We have proved that the shortest path between 2 points is a straight.
But we proved that our method gives us this result. So we can now apply the method without thinking.
Straight line. That's not actually what we proved. Here's what we really proved.
That's interesting. If there is a shortest path between 2 points, it has to be a straight line. Oh, but there might not be a shortest.
If there is a shortest path between 2 points, it has to be a straight line. I am not going to get into the subtleties here of this sort of necessary versus sufficient distinction, because there's a lot more complicated math that you have to do if you're going to deal with that.
This is incredible. I mean, people actually are alive that think in such details. This is unbelievable. This is magic.
I think we're going to content ourselves with knowing something about the solution if it exists, for the purposes of this 45-minute talk. All right, so let's sort of summarize the strategy that we engaged in here. We wrote down a functional in some way.
So this is the protocol. These are the steps. Recap our strategy. Write down a functional j of y. For example, we wanted the short, right? We're taking a function and we want the output to be the length of the function between x1 and x2, the arc length. Second step, construct a wiggle by adding variation. So the wiggle is the original y plus a times eta. Okay. Apply the functional to the wiggle. J of a is equal to j of y plus eta n, which is just w. He should have said that. J of a, well, it's j of w. This is w, isn't it? This is y plus a eta. This is w. This is j of w. But he's saying y and eta are held constant. As far as any j is concerned. Something like that. So j of a is equal to the function, he never said this, of x of y plus a eta, which is w, and w prime. I've never seen this. Take some kind of derivative. The derivative, what do you mean some kind of derivative? Derivative of j, assume y corresponding to a equals 0 is a minimizer. J prime of 0 is equal to 0. This is assume y is a minimizer. I never understood what he means by minimizer. But it's obvious that when a equals 0, j prime is 0 for a equals 0, obviously. Try to conclude something interesting about y. Try to conclude something interesting about y. Right, so we came to the conclusion, for example, that y prime equals k, therefore y is a straight line, yes. Because this is nothing to do with the straight line. This is any strategy. Whatever you wanna conclude, you can conclude. No one is telling you what to conclude.
We constructed a wiggle by adding a certain amount of variation. We fed that wiggle into the functional, and here's what we got. And that was truly some function of a single variable. And so we can do single variable calculus with it. We can take the derivative with respect to a. We're going to assume that we have a minimizer on our hands, come up with j prime of 0 equals 0, calculate, and then concluded something interesting about y. In our case, that y prime was a constant. Let's see if we can apply this strategy now that we've done.
I'm wondering how many views does this have? This is 1.8 thousand views, 5 comments. Yeah, I don't know how much more of this I can watch. I mean, this is good, but right now for me, it's not on my critical path. I just want to understand the principle of least action.
Now that we've thought our way through this whole wiggle and variation thing and gotten to the fundamental lemma, I bet that we can apply this strategy more broadly pretty quick. So let's think about how we could do that. Let's say that we just have some generic functional with some generic integrand here. If we do our whole, apply to a wiggle and take the derivative thing, here is what we're going to get if we write down that j prime of 0 equals 0. Well, the derivative of j is the integral of the partial derivative, right? Differentiating under the integral sign. What is that partial derivative going to look like? It's going to be weird. So f really depends on x, and it depends on w, and it depends on w prime. And x doesn't depend on a, but both w and w prime depend on a. And so then if we use the chain rule, we can write down an expression for partial f partial a.
Oh, okay. So this is now this is the Lagrange, I think. So f is dependent on x, w, and w prime, where w also is y and a and eta. He's not mentioning eta because eta is a function of x, I guess. So x, w, and therefore x and a. So we're not looking at eta, only at w. So we're saying the derivative, the partial of f with respect to a, because f depends on x and a, ultimately. So the partial of f with respect to a is the partial of f with respect to w times the partial of w over partial a, plus partial f partial w prime partial a. Interesting way of doing math with this tree. I've never seen this. How does f depend on a? Interesting. Because we're ignoring f partial x, because we're taking f partial a, because we're saying that j partial a equals 0 is 0.
which is this business. All right. And then, well, okay. So since w was y plus a times eta, that means that the partial of w with respect to a is going to be eta.
Okay, w is, I'm tired. W is y plus a eta prime, isn't it? I don't remember.
Y plus a times eta, that means that
Right, not prime. W prime is y prime plus a eta prime.
the partial of w with respect to a is going to be eta.
So the partial of w with respect to a, he should write it out. What is w? W is y plus a eta, so it's eta, and the partial of w prime over partial of a is eta prime. The partial of w, because w prime is y prime plus a eta prime. Y is irrelevant, so it's just eta prime. So now we can plug these back in.
And similarly, the partial of w prime is going to be eta prime. So we can throw those into this.
So we get the partial of f with respect to a is equal to the partial of f over partial w times eta, partial w partial a is eta, plus partial f partial y partial w prime times, well, partial w prime over partial a is eta prime, so eta prime.
Here, and here's what we get. And then we were really interested when a equals 0. And when a equals 0, w
A equals 0, j prime is equal to 0. No?
is just y, right? If we collapse out the amount of variation, we get our original curve back. That was sort of the point.
Yes. A equals 0, w equals a. Is that what he said?
Right? If we collapse out the amount of variation, so we can throw those into this here, and here's what we get. And then we were really interested when a equals 0. And when a equals 0, w is just y, right? If we collapse out the
Yes, w is just y because a is 0, so w eta goes away. So all you left is w equals y.
the amount of variation, we get our original curve back. That was sort of the point.
And we're interested in a equals 0, where w equals y plus 0 eta.
Sure. So then what, as far as we ever cared, partial f partial a is going to be partial f partial y times.
Because we're assuming w is basically y.
Times eta, partial f partial y prime times eta prime. Okay.
How do, like, everything we created should just disappear, but some things don't disappear. Ready for more integration by parts? Okay.
We're going to do some more integration by parts. Here we go. We are, I forgot a dx here. Pretend that's there. We were integrating the partial of f with respect to a. We can substitute in this thing that we figured out by the chain rule.
Why are we integrating? Why are we integrating? What do you mean we were integrating? I don't remember we were integrating. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There it is. So at 19, this was the integration. So dJdA is the integral of this thing. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So I guess this is the integration. I don't know.
I'm going to do an integration by parts here because anytime I see something multiplied by a derivative and I'm integrating it, I like to use integration by parts to get rid of that derivative. That often results in something nice happening. I think, again, the clear choice for dv is our eta prime, which means that v is going to be eta. And then that leaves partial f partial y prime to be our u. We are going to take the derivative of that with respect to x, which is weird.
The FDY, I mean, partial f partial y prime with derivative du with respect to x. Okay. I don't know what to say about all these things. This is very confusing. I have to figure this out though, because this killed me in general relativity just as much.
But that is what we got to do here because we are integrating with respect to x. All right, so then the second term, let's integrate by parts and put all the pieces together. Here is our uv.
So this is uv, okay.
Again, since we're evaluating from x1 to x2, and eta is a variation, this will die, it'll go to 0.
Mm-hmm.
And then we've got the integral of v du. Okay, so I'm going to take this blue thing and put it back in our whole.
Everything is blue. So that goes away, but instead we have that. Oh, that's blue. Okay. This is blue. Okay.
Big integral. And here is what I get.
Mm-hmm. This is becoming Lagrange. Euler Lagrange.
Notice that I can factor out an eta now. And that leaves me behind this red part. So I've got this red part, and it was multiplied by eta. Oh, but this was integrating to 0, which means that once more, we have landed in the situation of the fundamental lemma that we proved.
Oh, we proved the fundamental lemma. If the definite integral is 0, that means that the red must be 0 or a constant. In this case, it's 0.
Cool. This means that this quantity has to be identically 0. This is called the Euler-Lagrange equation.
Euler-Lagrange equation. If y is a minimizer for the functional j of y such that blah, 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 then y satisfies the equation df dy minus d dx of that equals 0, or df dy equals d dx of df dy prime. Mm-hmm. Yeah.
This is what we can conclude that's interesting about y. It has to satisfy this this partial differential equation.
Okay, this comes out of a functional. Okay.
I'm going to write it in two ways. Either that quantity that was multiplied by eta has to be 0, or, you know, if you just add this over, you can see the partial of f with respect to y has got to equal the x derivative of the partial of f with respect to y prime. hold that thought because we're going to see it again on the next slide. Okay. I want to think of a special case of this because in general, this partial differential equation is kind of hard to solve. And it's a little more powerful than we really need. So here's a special case. Look, I've got the derivative with respect to x of some other thing, and that feels weird to me. I think it might be useful for us to go back to our original integrand and think of its total derivative with respect to x. And so here again is this tree diagram. Looks very similar to the one we drew before, but this time we're looking at the dependencies on x instead of on a. So f depends directly on x, and it also depends indirectly on x through its dependence on y and on y prime. And so if we hit this diagram with the chain rule, we get the following. So the total derivative of f with respect to x is the partial of f with respect to y times the the derivative of y with respect to x. That's not partial because y doesn't depend on anything else. Okay, and then we got the partial of f with respect to y prime, and then the derivative of y prime with respect to x. And then we got the partial of f with respect to x that reflects f's direct dependence on x, maybe. Okay. So the thing that we just learned from the Euler-Lagrange equation was that the partial of f with respect to y is actually just the x derivative of the partial of f with respect to y prime. So we can replace this here with that.
That little thing becomes all of that. What? Wait. The f dy becomes this? And this is the rest of it? No, it's not. What is he replacing? What did he just replace? The f dx remains. This remains. This he just modified a little bit. But this thing, the f dy times dy dx. Oh, this is just dy dx. He modified names. Okay, and this thing becomes what he said. Okay, so it's just the f dy is d dx of the f dy prime. Okay.
Dy dx is y prime. Dy prime dx I'm going to call the derivative of y prime. Look what I got here now. I've got the derivative of a thing times something else. And then I got the thing times the derivative of the something else, which sounds to me a heck of a lot like the product rule, except I'm going to apply it backwards. And so
oh my god, this is a reverse product rule. Unbelievable.
That's what I get. That is just the x derivative, right, of this thing times this thing.
Wow.
So that's cool. And then I just have this partial of f with respect to x trailing out here. All right, so then if I just subtract this term over, I end up with this equation.
What do you mean subtract over? The f dx minus this thing. What's going on here? So this was the f dx is equal to, so again, the f dx. Oh, he's just moving this, subtracting over. Okay, got it.
Which I think you can see is true. So I said earlier that a lot of functionals that we care about are not going to depend explicitly on x because things are autonomous and don't shift, don't change when you shift from left to right. Right. So as long as the integrand of the functional doesn't depend on x explicitly.
In other words, the integrand of the functional doesn't depend explicitly on x. The functional doesn't depend on x. Of course not. It depends on a. How could it depend on x? It's you input a function over x. It should not depend. How could it depend on x? It's just a number. This happens frequently because many situations we'd care about are autonomous. Okay, so I think I understand what he means.
Explicitly, I bet that we're going to get a nice special case because this partial of f with respect to x is 0.
Suppose that the partial of f with respect to x is 0. What is f? F is the original function? What do you mean the partial of f with respect to x is 0? This I don't understand. In other words, the integrand of the functional, but f is not, it's not j. J is the functional. I don't understand. Okay, now I'm lost. 2653. No, no one asked any questions. This is a hand-wavy introduction to the calculus of variations. I talk about motivating problem, the catenary, solve an easier problem, minimal arc length, extrapolate a general approach leading to Euler-Lagrange equation and Bell, I don't know, whatever, and apply that general approach to the interesting motivating problem we began with. Also, you'll also see differentiation under the integral sign, a proof of fundamental lemma of the calculus variation, usual corollary differential equations, dirty tricks, and a surprising and very hand-wavy appearance of Lagrange multipliers. You can find my slides, a Beamer handout version on Overleaf. This way you can follow along and click on the embedded links. I hope you enjoy, and please feel free to contact me with questions which I may not be able to answer in any satisfying way. Jesus Christ, how am I supposed to contact him? But the f is not the functional. What is f? J is the functional. F is the line. F is the function. So whatever function, I don't get it. Say it again.
Then if I just subtract this term over, I end up with this equation, which I think you can see is true. So I said earlier that a lot of functionals that we care about are not going to depend explicitly on x because things are autonomous and don't shift, don't change when you shift from left to right.
This I didn't understand in the beginning, and maybe now it's coming back to haunt me. So I don't know what he means. I don't know what he meant. And why is it partial f to partial x? What is partial f? Should be, I mean, f only depends on x. Why would it depend on anything else? In other words, the integrand of the functional doesn't depend explicitly on x, but that's not f. I don't know.
Right. So as long as the integrand of the functional doesn't depend on x explicitly, I bet that we're going to get a nice special case because this partial of f with respect to x is 0. So here's what we've got. And we can think about just adding this back over now. And then integrating both sides, or factoring out.
Anyway, so df dx minus the dx of df dy prime, whatever, is this, which is 0. So this is the total df dx. This is a partial df dx. How could you have both? And then ddx of f, well, that's equal to 0. That means this equals that. So you can ddx out f minus df dy prime. Okay, that's fine.
out the derivative, quote unquote, and getting this, and then integrating both sides. And so we could conclude that f
integrate both sides. So just the inner part is equal to c
minus the partial of f with respect to y prime times y prime should equal some constant. And this is called the Beltrami identity. So this is a special case of the Euler-Lagrange equation in the case where the integrand doesn't depend explicitly on x.
Oh, so that has nothing to do with the Euler-Lagrange. That's fine.
Okay, fun. I feel like we now have some tools that we can confidently apply to
We're looking to solve the catenary, whatever.
situations that we may
Catenary.
find ourselves in. Let us return to the catenary. Sorry, that was a bad joke. We need to more precisely formulate the problem, right? Originally, we said like what shape, what function describes this curve that the chain takes. I think we're going to have to turn on our physics brain a little bit in order to formulate the problem more precisely. The operative thing here is that things generally in nature want to minimize their energy. And the particular kind of energy that we're interested in here is gravitational potential energy. If the chain is suspended from 2 points,
basically the system wants to turn, the system would like to convert all the potential into kinetic, as much of the potential into kinetic. The ball wants to roll down the hill, but it's constrained by the shape of the hill, so it can't go to infinite depth. It's limited by the depth.
it wants to hang in a way that minimizes the gravitational potential energy.
Right, the potential energy, very good.
There's also the length of the chain that we have to think about, right? If I have a longer chain, it's going to go like, woo, as opposed to a shorter chain that's going to go like. So here is a more precise formulation of the catenary problem. What function passing through 2 specified points, x1, y1, and x2, y2, with a specified length minimizes the energy, the gravitational potential energy? Okay. I'm going to need a functional. And again, we're probably going to have to...
That's very interesting. So least action just means least potential. The system wants to shed the potential energy, right? The system cannot hold on to potential energy. It wants to shed it within a constraint, within a geometric constraint.
Activate our physics brain for this. That's pretty common. Like I said, energy in this case is probably gravitational potential energy. We are going to slice, approximate, integrate again. We're going to think of a little chunk of the chain as a point mass, and then the gravitational potential energy of a point mass is the mass of that thing times acceleration due to gravity times the height that it has above the ground. Okay. Well, the mass of that little thing is going to be like the mass density of the chain times ds. Oh, look, there's that ds that I told you was going to show up again, multiplied by g multiplied by the height. I am going to assume here that the mass density of the chain is constant, which is a pretty decent assumption because otherwise things would get real bad. Okay, so I'm just going to rearrange some stuff here, pull my 2 constants out, and then I'm thinking of the height as y, right? Y of x, the function. And then ds was this that I told you to remember. Okay, neat. So then I just need to integrate that, and I get the total GPE of the whole chain. And in particular, since we're minimizing, we're just going to like take the derivative of this thing and set it equal to 0. These constants are just going to hang out, and then we can divide them over to the 0 side. So we don't even need those. So here's our functional. Now our integrand is y times the square root of 1 plus y prime squared. Okay. Well, that's neat. We can probably just I'm noticing that there's no x's in there, right? This is an autonomous situation. If I shift the chain from left to right, probably nothing is going to change because gravity is the same if you move 1 foot to the right. that means that we can use the Beltrami identity. All right, so we're going to need to do some calculations. We're going to need to figure out y prime, and no, I'm sorry. We're going to need to figure out the partial of f with respect to y prime. And then we're just going to multiply that by literally this symbol y prime. Here's our function. Here is its partial with respect to y prime. Notice as far as y prime cares, y is a constant. I'm doing this very formally. Yes, there is a relationship there, but just symbolically speaking.
Okay, what is he doing now? So f of y prime is, this is from before, okay. So the f dy prime is y, right, so this is 1/2 times that, okay, times 2y prime, yep.
Y prime considered as a different symbol than y is what we're taking the derivative with respect to. Do a little algebra, clean that up. Looks like
so y prime over 2 and 1/2 cancel out. 1 plus y prime square root. Okay.
like this. So then if I throw these pieces into the Beltrami identity, here is what I get. Here is my f.
So Beltrami, okay, so f, which is what we started with, minus the f dy prime, which is what we got, is equal times y prime. So it's squared is equal to constant, okay?
Here is my partial f partial y prime. Now that I've multiplied it by y prime, this y prime ends up being squared. Okay, and then the difference of those is supposed to be a constant. Neat. I'm going to clear that denominator because the square roots are freaking me out.
So multiply by the bottom square root, which is good. Yep.
I can now distribute this y through, and then
so y plus y prime squared minus everything else.
Some stuff is going to add to 0.
So then, what did he do? How did he get this?
I can now distribute this y through, and then some stuff is going to add to 0.
Some stuff adds to 0. I guess these two are 0, so y equals c. Y, so these two cancel out. So y equals, why is it y squared equals c squared? Oh, he's squaring both sides. Okay, so that's fine.
And so here's what I get. That's pretty decent. This doesn't look like too bad of a differential equation to solve.
Okay, it's a differential equation. What could satisfy
which is kind of surprising. Like, this seemed like a way harder problem than would just be amenable to attacking it with a simple differential equation. This is even a separable differential equation. Here's the algebra for that.
Okay, so y squared is equal to c squared 1 plus 1, okay, and then c squared, and so you multiply it out, c squared, yes, and then y squared is minus c squared, and that, okay, and then y squared over c squared minus 1 y prime squared, because we divide by c squared, and then y over c squared minus 1 to the 1/2 is equal to y prime. So take the derivative, I guess, of both sides or something. Dx is equal to,
I'm not going to talk through it because that's boring. You can
integrate this, but it's not nice. Wait, what about the last part? What is that? So you have y prime is equal to y prime. Well, y prime is just dy dx. So this is just dy divided by dx. So dy and then dx, and then he took this whole thing and he brought it here. So dx is equal to, you can integrate this, but it's not nice. So you have dx and that thing dy.
And integrate this. It's not nice, and I encourage you to try. There is a particular substitution that will make it nice, but I'm not going to say what it is for just a second. I wonder if there's another way that we could approach this problem, though. I like to say that differential equations is the study of dirty tricks. There's a very similar situation. Click on that link if you want to read the details, where the correct trick is a trigonometric substitution. And then we're going to work toward a parametric solution instead of an explicit solution. You can see if my y prime was, let's see, I guess a tangent of theta, then I got 1 plus tangent squared, and that should be secant squared, and then maybe some good stuff happens. So let's try that substitution here. I spun my wheels with this for a little while. I think you end up getting something.
Jesus Christ. So y squared is equal to c squared 1 plus tan squared theta. C squared secant squared y is equal to c secant dx d theta is equal to dx dy dy d theta dx d theta. So dx dy is 1 over tan theta because dy dx is tan theta. So dy d theta. Wait, dx d theta doesn't do anything. Dx dy d theta. Dx dy and then dy d theta. Wait, where did I'm lost. I'm so confused. How did he introduce theta into the picture? What do you mean y prime is equal tan theta? What is theta? What does that even mean? I don't know.
Something that works. If you make this substitution and dink around with it, you end up with this, which is a first order non-homogeneous differential equation, which is fairly straightforward to solve. This works. I think it feels like the wrong trick. I think there's maybe a cooler, funner trick that we can do. And let's see what that trick is. The trick is sinh and cosh. These are called the hyperbolic sine and hyperbolic cosine. Here are their definitions. They are related to our usual circular sine and cosine in a particular way. If you think hard about the real and imaginary parts of e to the ix, I think you can see what is going on. I'm not going to say too much about it. Here are the things that you care about from these definitions, and you can check that these are true. If you take the derivative of sinh, you get cosh. And if you take the derivative of cosh, you get sinh, which is like one step nicer than the relationship between sine and cosine's derivatives. And there's also sort of a Pythagorean-ish identity going on here as well, which is this.
Okay, this is becoming very tedious. I mean, it's good math, but I don't know if I want to get bogged down with so much math. This is very mathy, very mathy. I don't know. I used to know all this math by heart. This was so straightforward many, many years ago.
The square of cosh is equal to 1 plus the square of sinh. So this is close to the Pythagorean identity for sine and cosine, but sort of things are in different places. And in particular, I'm liking that I have a 1 plus something squared, because that was what my differential equation looked like. Okay, so here we go. I've got my 1 plus something squared. If I threw in like a cosh here, I probably win. No, I'm sorry. If I throw in a sinh here, I probably win. But there's also the c, and then let's see. If this was a sinh, then I think my y would have to be a cosh. I'm going to guess that y is the cosh of x over c. Let's see if that works. Y prime is going to be 1 over c times the sinh of x over c, which I'm hoping will sort of cancel out that c squared that we have up here. Let's see if that works. 1 plus y prime squared is this business, which I don't think is going to add up correctly. Let's see, if I multiply through by that c squared, yeah, I've got a c squared plus this, which is not quite what I want. I would really like that to be a 1, essentially, or this to be the same as some coefficient on my sinh squared. So I think that's probably the wrong guess. What if I modify my guess slightly? If I had a c here, then this would die. And so then when I multiply by the c squared, I think I would get a c squared plus c squared. So here's my revised guess, and let's see if that works. Yeah, okay, y prime now is 1 instead of 1 over c times the sinh of x over c. And if I add 1 to that, and then multiply by c squared, then I can do that Pythagorean thing, and I get that is indeed y squared. So hooray. I have managed to guess the solution to this differential equation by looking carefully at the structure and then knowing about the hyperbolic sine and hyperbolic cosine. Okay, this is cool. So I think that we have a solution, y equals c times the cosh of x over c.
What does that look like?
I don't think this is the general solution. I feel like we need another constant. I have a constant, but there were several parameters, right? There were several free choices that we had when we were setting up the problem. Specifically, the 2 endpoints. I could move any one of the endpoints around however I wanted. And so I feel like my general heuristic is that each free choice that I have ought to correspond in some way or help determine one parameter. So since I have these 2 free
But all right, yeah, this is not an introduction to the calculus of variations. I mean, now you're going into a very specific solution.
choices, I should probably have 2 parameters. Okay.
Or is it? I mean, is this this is like trig and stuff.
Okay. Another thing that I'm noticing here is that c that we had just came from like the Beltrami identity. It was a constant of integration for something a long time ago. It wasn't a constant of integration for the separable differential equation, right? So I think that I probably need like a constant of integration to appear somewhere. So here's another dirty trick. Notice that our differential equation was autonomous, right? It was invariant. It doesn't depend on x, and so it's invariant under horizontal shifts. And so
I don't know what that means.
probably if I just replace x by like x minus h to allow for horizontal shifts, that's probably all I need. And so I'm actually going to guess.
Okay. I don't know what else to say. I have to stop here. Let's see. How long have we been here? An hour and a half. Sorry, I have nothing deep to say about the universe. Let's see what we got. This is not interesting. Okay, let's see. Not interesting. Not interesting. Not interesting. Not interesting. I don't know. Wait, maybe.
Twitter co-founder. Why is social media so easily corrupted by the state? Twitter co-founder Jack Dorsey says guys like him are the problem.
I was a single point of failure. It creates a chokehold. You have a company, a CEO, a board that represents one place where an entity can put pressure on.
That was especially true during the COVID-19 lockdowns, when federal officials were in contact with every major social media platform, coercing them to remove content.
This was Trump. Wow, that guy is a complete idiot.
Even in normal times, Google and Meta collect vast troves of personal information on their users and receive hundreds of thousands of requests every year from governments around the world to access that data. When Dorsey was running Twitter, the company's Indian offices were raided after it offended a member of the ruling party. The government of France recently arrested Pavel Durov, the CEO of Telegram, and wants to hold him criminally liable for illicit activity taking place on the network. What if there were an alternative platform with no offices to raid and no single CEO to arrest? What if it were owned not by Mark Zuckerberg, Elon Musk, or the Chinese Communist Party, but by everybody and nobody all at once? What if there were no administrators with direct access to user personal data? That alternative exists, and it's called Nostr. Like Bitcoin, it's a community-run digital network highly resistant to censorship and corruption. If Bitcoin has the potential to serve as the foundation of a new global monetary system, Nostr could do the same for communication and identity in the digital sphere. Take it from Marty Malmy, who was one of the first developers to work on Bitcoin, collaborating with Satoshi Nakamoto himself. Now, he's a Nostr developer.
Bitcoin is freedom of money and Nostr is freedom of everything else.
When did social media get so broken? In what feels like a lifetime ago, Arab Spring activists used Twitter and Facebook to organize, coordinate, and topple long-standing dictatorships. It was intoxicating. But this tech-powered revolution from below was a mirage. Military regimes cracked down, and the very same networks that empowered the masses were repurposed as tools of censorship, surveillance, and repression. There are several decentralized social media networks that, like Nostr, aim to fulfill the same promise of community empowerment, but they're often heavily siloed, have integrated crypto tokens, and are funded by venture capitalists hoping for windfall returns on their investments. Handfuls of people are still in charge, making them overly susceptible to manipulation and control, just like the networks they're designed to replace. Nostr, by contrast, is open, simple, and ownerless. You control your own feed, and you choose what algorithms to use, if any. To join, you generate a public online address and a password that secures your identity. Then you choose which Nostr-compatible social networks or services to join. If you change your mind, you can migrate your identity and data elsewhere, which is vital for human rights activists and empowering for everyone.
I think the only reason people haven't really valued Nostr yet is because they haven't had that feeling yet. It's there, it's powerful, it's available for everyone.
The Nostr network is constructed like a spider web that can morph and regenerate, making it almost impossible to censor. If the Chinese government attacks Nostr
So it's peer-to-peer?
again, as it did last year, the network can spin up new connections constructed like a spider web that can morph and regenerate, making it almost impossible to censor. If the Chinese government attacks Nostr again, as it did last year, the network can spin up new connections. Marty Malmy predicts that eventually every conceivable app we have today will be built on Nostr. That includes payment services like Venmo. Nostr doesn't need its own crypto token because it integrates seamlessly with Bitcoin. Users routinely locate other people in the network's public directory and send them what's called a zap, which can range from a micropayment to $10,000 worth of Bitcoin. Like every financial services app, Venmo occasionally censors transactions and deplatforms users. But nobody can stop you from sending Bitcoin on Nostr. To pay or get paid, you don't need to fill out paperwork, and you could be located anywhere in the world. Nostr had only a small handful of users before Jack Dorsey started funding its development. Edward Snowden and the financial writer and investor Lyn Alden are among Nostr's biggest boosters. The entrepreneur and tech visionary Naval Ravikant recently endorsed Nostr, and the arrest of Telegram CEO Pavel Durov brought another surge of interest. Today, the network has more than 50,000 weekly active users.
Because it is coming, and it's just a matter of time and when we all decide to do it, when we all decide to remove these dependencies because we believe more in humanity than these companies and corrupt governments.
Social media is how we speak, transact, and shape our identities. We can't entrust our primary communication network to a handful of corruptible humans. And now, we don't have to.
Mm-hmm. 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 Andrew versus Timcast.
Killings. The Harris campaign further asserted that announced it over a week ago. We do
Really nice guy.
These guys are both extreme right wingers. What are they going to debate? Oh, they're not going to debate. They're just going to agree with each other endlessly.
Hear about your skills. Just go through and
They're just both going to dive into their same rabbit hole.
hello, Crucible Crew, and welcome to the Timcast IRL Watch Party. Hope everybody's having a wonderful day. Get to watch your boy Andrew cover the news of the day.
Okay,
with
I gotta go.
Cool, and Lord
I'm
knows
done.
there's plenty of news to cover.
All right. Okay, this was really boring, but I need to figure this out. See you tomorrow. Bye.